So the way it works, most of you know this because you've been here for a while, is that I'll start recording near the beginning of each session, and once I start recording, you can start typing your name into the chat so that we have a record for your attendance. In To keep getting data, you have to attend class, and by typing your name in, this is how we know that you've attended class. If you get data and you can't attend class one day, that's fine, but then your data you should use for the next week. Okay? So if you don't attend, then you may not be given data funds for the next week. So keep your data funds if you can't attend for some reason, and you can put them toward the next week of the class. Okay, so this is not news to most of you. And then we have a couple more people coming in. Looks like James and Theophilus are coming in. So welcome everybody to the last year of the program. I usually start by introducing myself, but I think there are only two new participants. I think only Matina and Victor are new, so most of you know me, but I'll give the quick introduction that I always give anyway. I started working in Liberia because of Asumana Jabate Randolph, who I met in the science labs at my high school, at Hunter College High School in New York City. And I started running three STEM workshops in Liberia in summers, in-person workshops, summer of 2011, 2013, and 2017. Most of the workshops were in Monrovia and Ganta, but we also did workshops out of BWI in Kakata, and then also made small trips to Cuttington University in Sokoko. So this is going to be the last year of the online I Help Liberia Mathematics Teacher Training Program. So it's always been a 5-year program from the beginning, and this is year number 5. I also helped organize Math Olympics contests for high school students in Liberia in summer 2013, 2017, and 2018. Some of you may know Clinton Quee. He's been a participant in some earlier years. He did the Math Olympics in 2017 and recently just completed his master's degree in mathematics in South Africa. So that was nice to see that from alumni of the contest. And then over the last 4 years, instead of writing our own contest, we've had a mathematics competition based out of South Africa called the WITS Mathematics Competition, which has had Liberian participants from Monrovia and Ganta over the last 4 years, and we've had a few people do fairly well there. And I think some of the teachers here are coaches for teams in that competition. Okay, so just about me. I've studied mathematics my whole life. I received a bachelor's degree in mathematics from Harvard in 2003, and then I did a doctorate in mathematics from the University of Pennsylvania in 2009. And I've taught at Columbia University and at the University of Virginia, and I've had a research visit in Germany at the Max Planck Institute also. And right now, I'm an associate professor of mathematics at Baruch College, which is one of the senior colleges of the City University of New York. So, City University of New York is a big college, 18,000 students, and it has several campuses throughout the city, and Baruch College is one of them. That's the one where I teach. And I do research in number theory and algebraic geometry, which maybe at some point later on in the course, I'll talk a little bit about what they really are, but it's not the main point of the course. Okay, so this is me so far, and so just what's going to be happening this year. So we're going to meet at 4:30 on Thursdays this year. We will always end class by 6:15. I have a meeting I have to go to at that point, so I'm usually going to try to stop talking by 6:05 or so, and by 6:05, and leave enough time for questions so that we can close the meeting at 6:15. Enoch, to answer the questions, yes, it was pure mathematics. That's what I studied. It was pure mathematics, both in undergraduate and graduate. So Deborah, who introduced herself, is always going to be the one handling the distribution of data, and she's going to be keeping records of attendance. So if you have data questions, you can always ask her. Occasionally, there may be other administrative tasks, and Sange Freeman and Abraham Jabate will handle a task every once in a while. Sorry, what happened to my Zoom here? What is going on here? Share. What? Oh no. Sorry, I got kicked off of the Wi-Fi network. Give me a second. No, what happened here? Sorry. What's going on with my Wi-Fi? Why is it taking so long to get onto this Wi-Fi network? Sorry, usually it's not me who has a problem with the network, but today I am. Um, that's my own network, right? Okay, join 882.022.0 and join. Net. Sorry, my iPad is having trouble with the network. My computer is fine, but my iPad, where I'm trying to do the workshop, is not so fine. I need to get my slides back. So give me 1 minute. What's going on here? Why can I not get on? My Wi-Fi not connected. Connect and stay on. Oh, good. Okay, let's try this again. All right, let's try this again. Okay, there we are.
Recording in progress.
Sorry, let me share one more time. Okay, sorry about that. Okay, so we're going to meet at 4:30 on Thursdays, and Deborah's going to handle the data. Uh, if you receive data and are unable to make a class, then you should save the data for the next week's class. I sent out a syllabus on the WhatsApp chat. I'll send it out again, but it has the meeting days on them, so they're all Thursdays, but we have these days in we have this September 11th and 18th, and then 4 days in October, 2 days in November, and 3 days in December. And I'm always going to post the video recordings of the sessions, so they'll be available on YouTube where you can watch them. I can't send the videos. Unfortunately, I can't send soft copies of the videos on WhatsApp because they're too big. They take up 100 megabytes or so. It's too much. They won't let me send it. But you can, if you have access to more data, you can always watch videos on YouTube. So I'll post them to the chat room. I'm going to post the links to the chat room, but I can't actually post the videos. I can only post the links. Um, Okay, so what are we doing this year? So most of you have participated in previous years. And the goal of the program this year, because it's the last year, is we're trying to make the progress achieved from the previous years sustainable. Okay, so we would like these types of workshops and teacher training to carry on even when I'm not leading things, right? So ideally, some of you will be able to lead similar workshops for other teachers at your school or other teachers in your city. Uh, uh, yes, so hopefully you can do that. And part of this year's program is to try to give you the tools to run similar workshops. Okay. So the fall semester, so this semester, we're going to focus on the mathematical aspects of being able to sustain the workshops. So we're going to look at a lot of topics that we've covered before in earlier years, right? So we've done logarithms, we've done trigonometry, probability, statistics, combinatorics, linear algebra, calculus. Probably not going to do calculus this year, but we've done geometry. We've done lots and lots of topics, and we're going to go over many of them. That are all from the high school math curriculum. I noticed that not everybody is a high school teacher, but this workshop is really for the high school curriculum, and that's what we're going to focus on. Um, so that's what we're going to focus on. And so we're going to have topics that have been covered before, but I'm not just going to teach them. Like in the previous years, I said, here's a topic, let's learn it, right? The idea here is that now you've kind of seen the topic already, okay? And instead, what we're going to do is try to discuss tools for teaching the topic effectively. So we're going to look at these topics from the perspective of a teacher instead of from the perspective of a student. Give me 1 second. Okay, so from the perspective of a teacher. And one of the things I want to do is take you behind the scenes in my thought process for developing the program. So when I was teaching a lesson on trigonometry, what was I thinking when I structured that lesson? Oh, you got to be kidding me. Am I off the Zoom again? Uh, what's going on with this Wi-Fi? But um, this is annoying. Why does my share keep going away? Okay, this keeps logging me out of Zoom.
Recording in progress.
Sorry. Let's try this again. Okay. I don't know what's going on, but something's going on. But in any case, we're okay. So I'm going to try to take you behind the scenes in my thought process for developing the program. And what's the philosophy, right? The philosophy is that a teacher should know more than the average student is expected to learn, right? If you're going to teach how to do some algebraic equations or some kind of rule in mathematics, to be the most effective that you can be, you don't just want to know exactly the thing that you're teaching. You want to know a little bit more, okay? That helps you in general. It helps you to be able to make clear presentations. It helps you to be able to answer student questions effectively. Students might have questions about a difficult problem or about what something is used for or about how to apply something. And the more you know, the better you'll be able to handle, a question like this from a student. So, and in particular, a teacher should know how to do more challenging problems than the average student will encounter. And what's even better is if a teacher knows how to ask more challenging problems than the average student will encounter, right? Because you're going to have some very good students and maybe they'll want a challenge. And even if you don't, it makes everything much easier for you to teach if you're thinking on a bit more advanced level than what you're actually teaching. So it's even better if a teacher knows applications of the given topic, even if there's not a lot of class time for them, right? Because it's good to be able, a student asks you, what's an application of this? You want to be able to give them an answer. So, kind of looking forward to the spring semester. So, in the fall, we're mostly focusing on the mathematics. In the spring, we're going to focus a little bit more on presentation and practical strategies. How might you run a workshop? This may, I have to feel out over this semester what is the feasible technology that everybody has access to, or do we have certain technology centers that people can go to in order to give a workshop, for instance, online? Or is everything going to be in person? And even if it's in person, is there good kind of projection technology that we can use? But so, for instance, I might, if there's demand, I might have a few sessions on how I make these slides. I can teach you the program that I use. It's called Beamer. That's how I make these slides. And to the extent that technology permits, and I know this is difficult because it requires, reliable data and internet, we may try to have the participants give some presentations. That will be later on in the spring. Doing that will probably have to take place at some kind of central area at a school or a ministry or somewhere like that. So, I'm going to be talking to people and figuring out how this should work in the spring. For the fall, it's still going to be kind of traditional. I'm going to give the presentations, but the focus will be a little bit more from the teacher's perspective. And I'm just about worried that I am going to go get my live presentation it's like my Zoom keeps logging out for like a minute each time. I don't know what's going on with this. Uh, sorry. Yeah, this does this even work? Ugh, sorry. I don't know what's going on with my network here. I need to I need to try this again.
Recording in
Okay, I keep getting these notifications that my iPad is losing connection to Zoom. I don't know why that's happening. Okay, so this is basically the plan of the semester, the plan of the year. So the first semester will be mostly math, might bleed into the second semester a little bit, and then we're going to talk a little bit more about presentations and practical strategies in the spring. Okay, so all right, so let's start off with a little bit of math. We have about an hour to do some math today. And so as a sample topic, just a thing to start with, not because it's necessarily the most important topic, but I want to talk about rules for logarithms and exponentials. And this is actually the very first topic that we did in the workshop way back in 2021 when we started the workshop. Okay? So let me just recall, what these are. So if we have a positive number a, such that a is not equal to 1, then we have this function called a logarithm. Okay? And the logarithm to base a is the inverse function to the exponential function a to the x. And this is, what's the notation for this? Why is this not writing? Sorry. What is going on here? No, 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 no. No. The notation for this is the logarithm of x to base a. We write a little a down there. Okay. And this is kind of a short way, but it's kind of easier to understand by examples. So since 10 squared equals 100, we write that log 10 of 100 is equal to 2, right? The way that we think about this is log a of x means, what power must a be raised to get x. Uh, to get x, okay? So, right, so log 10, 100 is saying what power do you need to raise 10 to in order to get 100? And so in this example, it's 2. Okay, I'm assuming that most of you have seen this. I'm not going to be doing a comprehensive lesson on logarithms right now. I can always give more practice if people want it. Okay. So So what I want to do is ask certain questions that, as a teacher, if you're going to teach this topic. So I think this is in the 11th grade curriculum. So I looked at it in the Liberian curriculum. I think this is in the 11th grade curriculum. So first of all, why doesn't this work for a equals 1, right? So why can't I do, so what happens if I try to do, let's say, log 1 of 6? Why doesn't this work? Why doesn't this make sense?
Yes. Yeah,
Yes,
that's
enough.
right.
Yeah,
Yeah, in this context, it won't actually work because if you raise one to any power, like if you raise one to the power of any integer, for example, one raised to the second power, one raised to the fifth power, it will still come down to one. So
exactly.
yeah, so if you are saying, for example, one raised to the power of two is equal to 100, it means that it does not make sense because one raised to the power will still be one, and you can't get one to be equal to one, so that statement will actually be false.
Right. Exactly. And not just to any integer, but even to any real number. 1 raised to any real number is going to be 1. So log 1 of 6, this has to be undefined because because you cannot solve 1 to the x equals 6. Okay, you can't solve this. Okay, so log 1 of 6 is going to be undefined because it's asking you what do you raise 1 to in order to get 6? And the answer is there's no answer, right? 1 raised to anything is going to be 1. Okay, So this is just a good thing to work out. You can't define log with any base that you want. In general, we really don't define it with negative numbers as the base either, and we don't define it with zero as the base either, because you can't do zero to the x equals six, right? I mean, zero to the x equals six is zero to anything is zero, so you're not going to be able to do that. And you don't want to use negative numbers either for logs because raising negative numbers to things that are not integers gets very dicey. Like already, minus one to the one half. That kind of means a square root of minus one, and then you're getting into complex numbers and imaginary numbers. So, logarithms with negative numbers is pretty subtle and generally is not part of the high school curriculum. So we're always going to assume that our base for the logarithm, this is called the base here. This is the base, this 10 right here, base, is always a positive number, not equal to 1. Okay, so now, if you recall, there's a whole bunch of rules that go with exponentials and logs. There's a whole bunch of formulas that work with exponentials and logs. So you have your exponential rules. So these are the ways that we simplify exponential formulas. So if you've been in the program, you've definitely seen these at some point. So when you add exponents, you multiply the numbers. So a to the b plus c equals a to the b times a to the c.
Hello, Dan.
Hello, yes, Prince.
Yeah, please zoom the screen some, please.
Okay,
Zoom the screen.
okay. All right.
Okay.
So rules of exponents here, a to the b plus c equals a to the b, a to the c. A to the b minus c equals a to the b divided by a to the c. A to the bc equals a to the b raised to the c. What does it mean to raise to the 1 over b power? That means to take a bth root. And then anything raised to the 1 is itself. Anything raised to the 0 is equal to 1. Here, I guess we need to have that a is not equal to 0 here. 0 to the 0 is undefined. And then a times b to the c is equal to a to the c times b to the c. So again, these are all rules you've probably seen before. I'm not going to spend a lot of time on each one, but the point is there are rules that allow you to simplify expressions that use exponents. Okay, and similarly, every exponent rule has a
Yeah,
corresponding log rule. Yeah, Emmanuel?
yeah, excuse me. How are you?
Yes. Good, how are you? Welcome.
Yeah, okay, thank you for the class.
Yeah.
I have a question.
Yep.
Okay, there is a common question that I ask. For example, what is the explanation if 0 is over 0 undefined? What better explanation can we give our students
For 0 over
when
0
the question is
undefined.
asked?
Let me
Yeah,
answer this.
or 1 over 0 undefined.
Okay.
What is the explanation mathematically, sir?
Can I answer that at the end of the class?
Yeah,
It's
okay,
not
no
it's
problem.
not completely
Yeah.
germane. So ask me again at the end of the
Okay.
class and I'll answer.
Okay,
Okay?
okay, thank you.
Okay, sure. So when I finish up a little bit after 6 o'clock,
Okay,
okay? Great.
thank
Okay,
you.
so similarly, so we have these rules of logarithms. For now, we can just take them as rules. So for instance, the log if you fix a base, so here again, you're always having that a is greater than 0 and a is not equal to 1. Your base has to be some positive number that's not 1. So the log a of x plus the log a of y equals log a of xy. Log a of x minus log a of y equals log a of x over y. And then we have some other rules. The log a of, I should put this in parentheses, x to the r is equal to r times the log a of x. The log a of a bth root of a is equal to 1 over b, right? That's, remember what log means. It's saying what power do you need to raise a to get a bth root of a? And the answer is you raise a to the 1 over b. That means taking the bth root. So this would be here, b would be equal to 1, 2, 3, 4, 5, etc. The log a of a is 1 because a to the 1 equals a. And the log a of 1 is 0 because a to the 0 equals 1. And then there's a seventh law, a little bit more complicated, which is in general, if you're trying to take the log of a to base b, then you get that if there's any other number c, that's the same thing as the log of b to base c over the log of a to base c. And the important thing is for a calculator, you can take, if you have a scientific calculator, you can take c equals 10. Log 10 is what a calculator means when it says log. So you can take c equals 10, and then what you get is if you want to calculate log a to base b, you can say that that's log of b to base 10 divided by log of a to base 10. And these can be done on the calculator. Right? So you have a button on the calculator that calculates base 10 logarithms on a scientific calculator. So if I want to know what is the log of 72 to base 38, then the calculator can't do that. Instead, you say, what's the log of 72 to base 10? And you divide it by the log of 38 to base 10. Okay, now with the internet, if you have internet access, then the calculator is not so important. If you want to know what the log of base of 72 to base 38 is, you just type what is the log of 72 to base 38, and Google will answer you, or ChatGPT will answer you, or whatever. But if you have just a calculator, then this is a helpful thing to do. Okay, so again, I don't want to go over memorizing the laws right now. Okay, let's just acknowledge that we have these laws. And if you're teaching a lesson on the rules of exponents or the rules of logs, then you're going to know these laws, right? That's kind of the minimum that you need to teach the lesson. If you're going to teach some laws, some rules, then you need to know what the rules are. Okay? Great. Okay. So, I mean, just a quick example, just so this isn't completely abstract. So if I take the log of 25 to base 5 plus the log of, 125 to base 5, well, this is equal to, well, I could calculate it explicitly. This is just 2 plus 3, right? Right, because 2 is what you have to raise 5 to get 25, and 3 is what you have to raise 5 to get 125. And so that's going to be equal to 5. But alternatively, you could use the rule of logs, and this is going to be log base 5 of 25 times 125. And that's going to be log base 5. It turns out if you take 25 times 125, that's going to be 33, what is that? 3125. And this turns out to be 5. It's the same thing. Okay, so you can multiply the arguments together, or you can just take both of the logs separately and add them. Either way, you get the same answer. Okay. All right, so we have these rules. So now a student might be expected to execute straightforward applications of the rules. So what's a straightforward application of these rules? Okay, that would be, something like this. Let me just erase that. That's not supposed to be there. So evaluate 3 to the 100 divided by 3 to the 99, right? I mean, this is a very straightforward question, right? We use the rules of
So
exponents. Yes.
yeah, so if you use a
Sure.
rule exponent, the answer will probably be just one. It will just
Exactly.
be three.
Right, so if you use the rules, this is just 3 to the 100 minus 99. The exponents subtract, which is 3 to the 1, which is 3, right? So that would be a very straightforward question. Another straightforward question, just to see if you understand the definition of log, what is log of 16 to base 2? Right, so what is...
So the answer, it will be 4.
Right, and that's because you're asking what do you need to raise 2 to get 16? That's because 2 to the 4th equals 16. Okay, now another thing would be, so what about log of 99 to base 3 minus log of 11 to base 3? These are not things that are easy to figure out on your own, right? What power do you have to raise 3 to get 99? I don't know exactly. 4 point something. And same thing, what do I have to raise 3 to get 11? I don't know exactly. 2 point something. But yes, Rash?
So the 99, if we use the quotient rules, which is the division rules, right?
Mm-hmm.
We still can also arrive by saying the log of 99, taking one of the logarithm now,
Mm-hmm.
which is the log of 99,
Mm-hmm.
the log of 99 divided by 11 base 3.
Exactly.
So we will just have 2 the answer now in our case.
Right. So now, and this is much easier, right? Because this is 99 divided by 11 is 9. And then, as Rash said, the answer is 2, right?
It's just
3
two.
raised to the 2 is 9, right? And then another thing a student might be asked to do in an algebra class is you take something like this, and the student needs to simplify this using the laws of exponents, right? So I'll just do this one myself. So if we have x to the fifth times 2x to the 3 divided by 4x squared, well, this is just x to the fifth. Well, the 2x to the 3 is 2 to the 3 times x to the 3. And then you divide it by 4x squared. That's 4 squared x squared. And if I write out what is this? This is, if I combine everything in the top, I have 8x to the eighth. And on the bottom, I have 16x squared. And then I can do, sorry, let me just mute everybody. And so then if I want to do some cancellation, I can cancel out the 8 and the 16, and I'm left with a 2 here. And we know that when we divide exponents, the exponents subtract. So I cross out the 2 and the 8, and I get a 6 here. And so what I'm left with in the end is x to the 6 divided by 2. Okay, so I guess I should say this x squared cancels out completely with the 8, and it becomes a 6. Okay, I'm going to just scroll out. I understand that the writing is a little bit small here, but the point is these are all very, very straightforward applications, right? It says you have an expression, you want to evaluate it, or you want to simplify it. You use one rule or one definition. It's always very, very clear exactly what the rule is to use, right? I mean, here you've got to use the quotient rule for exponentials. Same thing here. You use the quotient rule for exponentials, and you also use the kind of distributive law that 2x cubed means 2 cubed times x cubed. Here, you have to use the subtraction rule for logs, and here you're just evaluating a logarithm. And so if this is what a student can do, they might be able to do okay on a test. And if they were taking the WAS and there was an easy log or exponential question, they might be able to get it right. But if the question gets a little bit harder, or if they have to do any application, then they're going to need to know more than just this. Okay, so if this is all that somebody can do, then you could say they have a basic understanding of the rules of exponentials and logs. But you can't say that they have a deep understanding. Okay, a deep understanding means you have to be able to do a little bit more than this. All right? And so what do I mean by doing a little bit more? Okay, so what's the next level? Right? So what other elements might we ask for in a student's or a teacher's understanding of the exponential and logarithm rules? So the first one would be, can he or she apply the rules correctly when the numbers are more difficult to calculate with, right? I mean, everything here we could do in our heads. We didn't need to, we log 3 of 9, log 2 of 16. These were all pretty easy. All of our exponential subtractions and addition were easy. If the numbers get more complicated, can they still, stay calm and apply the rules, right? So that's one thing that you could say is a next level task. Another thing would be, can he or she combine the rules with, I wrote here with solving algebraic equations, but what you really want to know is, can you combine the rules with just other parts of math? Like a math problem, especially anything you might encounter in an actual application, is not usually going to be one tiny little piece. It's usually going to involve a few different things. And in one part of the problem, you might need to use an exponential rule. And in one part of the problem, you might need to use a logarithm rule. So can you combine these rules with other types of things? So in particular, maybe with solving an algebraic equation. So that would be a next level task. Third thing would be, can the student or the teacher use context to figure out which rules to apply when it's not so obvious, right? The way I set up these problems over here, it was very clear exactly what rule to use. You look at your list of rules, you see the one that works, that's it. But there are problems where maybe it's not as easy to tell which rule to use. And can the student or the teacher figure that out? And then the fourth, maybe the deepest level is, does the person know why the rules work? Right? Are they just given from God, or is there a reason for why they work? Okay? And if you can do these things, then I would say you have a very good understanding of exponential rules and of log rules. And I would say if a teacher wants most of the students to get even the basic understanding, it's helpful for the teacher to have the deeper understanding. Okay? And maybe not every student will get the deeper understanding, and that's okay. But you want at least some students to get that. And regardless, when you're teaching this, having the deeper understanding is going to make your teaching much more effective. Okay? So what I want to do for the rest of our time today is I'm going to go through some sample problems that demonstrate each of these extra techniques. And these are things that if I'm making a workshop, especially for teachers, as opposed to if I'm teaching students a basic lesson, then I might only just do a lot of practice with the basic stuff, which is fine when you're teaching a basic lesson and you're introducing a topic. But if I'm doing a workshop for teachers, I'm going to want the teachers to wrestle with these more difficult aspects of being able to do the topic. And today, the example is logarithm rules and exponential rules, but you can usually apply this kind of thought of what is the next level to many different areas of mathematics. And over the course of the semester, we're going to do that. We're going to think about all of these different areas and be like, what do you really need to know to have the correct depth of understanding to be, a versatile teacher, to be able to answer questions that your students are going to ask you correctly, and to be able to, tell students something more if that's what they're asking for. Okay? So these are, for me, I would consider kind of next level tasks as compared to these, which are the real kind of very straightforward applications of the rules. Okay? So, okay. Number one, more difficult numbers. Okay? So, innocent looking question. Compute log of the cube root of 9 to the base square root of 3. Okay? Structurally, there is nothing different between this question and compute log of 16 to base 2. But we don't have just basic numbers anymore. We've got square root of 3, cube root of 9. I mean, these are perfectly good positive numbers, but you're not just going to look at this and tell me the answer, right? I mean, you look at log 2, 16, you can just look at it and say, oh, 4. This is going to require at least a little bit of work to think through how to do, right? And so usually your strategy when you have more difficult numbers, something like this is, can we make the problem easier using a log rule? No, let me not be so colloquial, using a logarithm rule. Okay, can we make the problem easier using a logarithm rule? Okay, and so we've got log to base square root of 3 of cube root of 9. Okay, so let me go back. Okay, well, here's our logarithm rules. Well, what kind of looks like it might be applicable, right? We have our rule bank that because we've mastered our basic tasks, we know these rules, right? But what I've got here in the argument for log is cube root of 9. So it looks a little bit like this, although that's not exactly right, because that would be if I had log base 9 of cube root of 9, whereas what we actually have is log base.
Yeah, that was.
Yes,
Yeah, the problem that I want you to switch to the problem. I want to fix on. I want to get something light on it.
Okay, ya pues.
Sorry, Rush or sorry.
Yeah, so yeah, like the problem there because if you are seeing the base there is just is the square root of 3,
Mhm.
and the problem there is the cube root of 9. So what's there? The simple way is that if you see the square root of 3 now, that 3 can be written as 3 to the power 1 over 2. and you can take that 1/2 to bring it in front. The coefficient for the log will just be 2. Then the problem itself, the problem that are inside the log there is 9 raised to the power 1/3. So the 9 raised to the power 1/3, it can be written as 3 raised to the power 3/2. So now the 2/3. So that entire stuff, you can bring out the coefficient 2 as well in front there. So it will be 2/3 times 2. So it will be 4/3.
All right, so this is going to work. So let's go through this slowly. So the main rule that you're using this rule over here, right? You have this 9 raised to the 1/3 is this cube root of 9. And what this rule says is that we can move that 1/3 outside, right? We can move that r. It goes from the exponent to something that's multiplied outside the log. So if we go back to our question, then we have, well, this is going to be equal to log to base square root of 3 of 9, and well, I'll write this as 9 to the 1/3. I'm just rewriting cube root of 9 as 9 to the 1/3. And so this is, I'll call it, so I can move the 1/3 over, right? And this will give us 1/3 log square root of 3 of 9. I don't know why does this keep doing this? What? Sorry, I'm just getting very annoyed at my iPad right now. I think this has something to do with the case. Okay, so this is it. And then, right, and so then what Enoch said, so you could write this as an actual rule. You could say, oh, this is square root of 3, that's 3 to the 1/2, and so, that's going to be, you're going to have to multiply by 2. But even if you don't know that rule, at this point, you could say, if you want to rewrite everything in terms of 3, right? This is 1/3 log base 3 to the 1/2 of 3 squared, right? And so now what does this mean? Right, what is going on here? Okay, so it's like, what power do you raise 3 to the 1/2 to get what is going on with this pen? I'm sorry, my technology is really bothering me today. To get 3 squared. Right? So, I mean, another way of thinking this, we're trying to solve, 3 to the 1/2 to the x equals 3 squared. And now we know from rules of exponents that that's the same thing as saying 1/2 x equals 2, which is the same thing as saying that x is equal to 4, right? Because 3 to the 1/2 to the x is actually 3 to the 1/2 x. So this is giving us 1/2 x equals 2, and this is giving us x equals 4. And so what that means is that this expression right here is really 4. And so exactly as Enoch said, that gives us 1/3 times 4, and that's going to give us 4/3. Okay? So what we see here is that we have a question that looks innocent. It looks like log 2 of 16, but with more difficult numbers. And what happens with more difficult numbers is that doesn't just mean you have to add or multiply bigger numbers. It means that you sometimes need to use other rules to get an expression into the way that you want, right? So here we had to use the exponential rule for logarithms. We had to use the composition rule for exponents in order to solve for x equals 4. Alternatively, you could write another rule of logarithms using the base that I didn't write. Or we could say that this is log 3 of 9 divided by log 3 of square root of 3. There's multiple ways to do this problem. But in the end, you had to do something more, right? So a student who's only has like the basic knowledge of how to do, basic logs with easy numbers is probably going to have quite a bit of difficulty with this question. And the student hasn't necessarily internalized those rules. Okay? So this is kind of the first aspect, how can a question be more difficult than just the basics? Okay. Questions on this example? All right. Example 2, what's the next thing? We said combine with algebraic equations. So you could have something like this. I have to look at some old WASs. Deborah's going to get them for me. So I need to know what kinds of questions show up on them. But on like American standardized tests, for instance, this is a type of question that you always get. Okay, this is a type of question that they're always going to give you. So solve the equation log base 4 of x plus 1 plus log base 4 of x plus 4 equals 1. And this is a type of question that always shows up on exams that I've seen. Okay, so what do we have to do this, right? We're going to need to use, all of these are going to use a rule, right? And the rule for logs that we have going back to our, this involves adding two logarithms, right? So clearly we're going to have to use this addition rule in order to solve it, right? Log a of something plus log a of something else equals log a of their product, right?
That was that.
Yes, Rush?
Joy, I don't know whether it's for the equation what I have on my paper, which is s can be 0, s can be -5, something like that.
Okay, yeah, so we'll get to that, right? So that's correct, basically. But only one of those answers is going to work. Okay, so yeah. Yes, Rush.
Yeah, for the answers in just code, they are all correct, but for the -5, you will see that, to every math problem, the application is it should be proofable. So now, if you see that if you put 0 in the equation, it will be proving that the entire thing across the equation on the left side will be equal to the right side, which will be equal to 1. But if you put 5 there, it will not give you 1. So the answer selected for this one is probably 0. Acceptable.
Yeah, so that's going to be right. So remember, let's use the rule of logs, right? So how do we get to that? Well, we're going to use the rule of logs. We're going to use the addition rule.
Yeah.
Right. So this is going to be log base 4 of x plus 1 times x plus 4 is equal to 1. And then if we're going to say that log base 4 of something equals 1, what does that mean? It means that 4 to the 1 equals this. Right? So this is going to tell us that 4 to the 1 is equal to x plus 1, x plus 4. And so now this is a quadratic equation, so we can write this down. This is 4 equals x squared plus 5x plus 4. And that's going to give us, why does it keep doing this? Okay, this is going to give us, 0 equals x squared plus 5x. And this is going to give us 0, we factor this, x times x plus 5. And this is going to give us two solutions. So it's going to say x equals 0 or x equals -5. All right. So there's a subtle point here, which is something that I didn't really realize until I had been a professor for a little while. What does it mean to solve an equation? Okay, so this has to do a little bit with logic. So when you're solving an equation, what you're saying is that if this is true, then this is true, and that implies that this is true, which 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 implies that this is true. Solving an equation is a set generally of, it's a list of one-way implications. Something implies something else, implies something else, implies something else. So what we have, proven here, it's really a proof. We've proven that if log base 4 of x plus 1 plus log base 4 of x plus 4 equals 1, then x equals 0 or x equals -5, right? What we have not proven is the backward direction. We haven't proven that if x is 0 or x is -5, then log 4 of x plus 1 plus log 4 of x plus 4 equals 1, right? Solving an equation, everything we've done is a one-way if-then statement, right? So do some formal logic, but it's really, if this is true, then 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 this is true. And it is true that x is 0 or x equals -5. So this tells us what x is to look at, But now we have to go back and try them to see if they actually work. Okay? And what happens here is that if we do x equals 0, we try to punch that in, and we get that log base 4 of 0 plus 1 plus log base 4 of 0 plus 4, well, that's equal to log base 4 of 1 plus log base 4 of 4. And well, log base 4 of 1, that's saying what do you raise 4 to get 1? That's 0. Log base 4 of 4 is what do you raise 4 to get 4? That's 1. And this is going to be 1. So this is good. If we punch in x equals 0, we get the right answer. Now, what happens if we punch in x equals minus 5? Well, we have log base 4 of minus 5 plus 1 plus log base 4 of minus 5 plus 4. That's equal to log base 4 of negative 4 plus log base 4 of negative 1. And now we've got a problem, right? Because logs are not defined for negative numbers, at least not if you stay within the real numbers. Log base 4 of negative 4 is saying, what power do you have to raise 4 to in order to get minus 4? Okay? And the answer to that is it's kind of meaningless. Raising 4 to any real number is, it's going to be, I have a pi I or something, I think.
Yeah, it was something like 2I, yeah.
Yeah, I think it's what's it going to be? It's going to be like something with absolute. It's going to be like it's going to be yeah.
Just
What's
now,
it going to be for negative 1? I have to think about it a little bit. Yeah, I think it's just going to be I. It's just going to be I. Yeah, to the 4 to the I is I think going to be minus 4. I have to think about that. That may be wrong. I have to, but in any case, this is leaving the realm of high school mathematics to deal with negative logs here. Okay, so the point is this here, as far as the real numbers go, which is generally how these functions are defined in tests, this is going to be undefined. Okay, this is going to be undefined, which means that this x equals minus 5, if I punch in x equals minus 5 over here, I don't get 1. I get something undefined, which means minus 5 is not going to be a solution, right? So the only valid solution is x equals 0. Okay. So there's kind of two things going on here. One is you're tying in logs with algebraic equations, with quadratic equations, so you have to use both techniques. And the other thing, which is a little more subtle, is you're dealing here, you're really encountering what is the logic of solving an algebraic equation. Okay, and the logic of solving an algebraic equation is you're making one-way implications which tell you if this is true, then x equals 0 and x equals minus 5. But if x equals 0 or x equals minus 5, they might not both actually make it true. Maybe only one of them will make it true. Maybe neither one will work, right? So the logic is what's telling you that you actually have to check, right? And a student who's going too fast and is just applying the rules and doesn't understand what they're doing, they're going to say x equals 0 or x equals minus 5 are both solutions, and that's going to be wrong. Okay? So this is another, I'd say, kind of second order thinking process that you have to be able to do to answer a question like this. Okay. Any questions? Okay. Great. Okay, good. Example 3. So what rules to apply, right? So let's say that I'm going to tell you that x is log of 3 to base 2 and y is log of 5 to base 2. And so I want to say evaluate the following expressions in terms of x and y, right? And maybe just so that I don't have to keep scrolling back, I'm just going to rewrite, I'm just going to rewrite a few of our rules of logs, right? So log a of x plus log a of y equals log a of xy log a of x minus log a of y equals log A of x over y. I'll say log A of B is equal to log C of B divided by log C of A. These are probably the most, and then maybe log A of A equals 1. Okay, so these are going to be the most important rules. I'm just going to copy them down over here. Okay. So this is 4 different questions that we need to evaluate in terms of x and y. And it's not really telling you, these are all just numbers, right? So it's none of this stuff is in the form of an actual rule, right? So let's look here, right? So we have log 2 of 15. All right. So this one's not so hard, right? Because we're given log 2 of 3 and we're given log 2 of 5. So here, right, we have a straightforward application of the rule, which is that if we add log 2 of 3 and log 2 of 5, then we get log 2 of 15. We get what you get when you multiply them, right? So this is going to be just x plus y. Okay. Okay, so that's maybe number 1 is a pretty straightforward application of the rule. You have to recognize that 3 times 5 is 15, but you don't have to do that much else. Okay, what about something like example 2? So log 2 of 7.5.
Hello?
Yeah, you rewrite it as a
Right.
fraction.
Oh, sorry. Who's speaking? James. James. Yes. Hi, James.
I have to rewrite it as a fraction.
Right. Good. So to rewrite this as a fraction, we have. Why is this not? Why is this doing this? Why? I need to change. Something's weird with my settings. Okay, this is log 2 of. So as a fraction, instead of 7.5, that's 15 over 2. Great. And so what are we going to do with that? James, do you want to continue?
15 over 2. You express 15. Express 15 as a product of 3 and 5.
Right. So that's log of 3 times 5 divided by 2.
Yeah.
And now what rules do we use at this point?
Use the product rule.
Right. We use the product rule and the quotient rule, right? So this is 3 times 5 divided by 2, right? So that'll be, this is log 2. So log 2 of 3 plus log 2 of 5 minus log 2 of 2, right? And now we know what this is, right? Because log 2 of 3 is x, and log 2 of 5 is y, and log 2 of 2 is just saying, we have the rule, or it's saying, what do you need to raise 2 to in order to get 2? And the answer is just 1. And so this is what we have here, right? Good. So the answer here is x plus y. The answer to here is x plus y minus 1. Good. All right, great. Yes, Rash, question?
Yeah, all right. I just wanted to just say something like Petini, maybe you are solving a problem, like maybe it's not uniform. In uniform, like saying that 7 raised to the power x plus 7 raised to the power x plus 7 raised to the power x equals to 147 in that case. So, all right, because see some people use different methods. I don't know. Yeah.
Okay. Yeah, we can do a problem like that next time. I think we won't have time for that today, but we can do a problem like that next time.
Okay.
Yeah. Okay. So, okay, let me just for time, because we only have about 10 more minutes, let me just go through these other things. So log 3 of 5 here, we're going to have to use this rule. Sorry, yeah, Enoch.
Yeah, that one, it will be the rule of log x plus log y minus log, it will be minus log x.
Let's be careful. I think we'll just use this rule, right? Which is that you can always change the base.
Yeah,
if you want to, right?
it's the same thing I think.
Okay.
Yeah.
Right. So let me just write this anyway. So this is going to be, we know that this is equal to log 2 of 5 divided by log 2 of 3. And that we know is just going to be y over x. So that's our solution here to number 3. And then lastly, number 4 is a little bit harder. So what about log 5 of 6? Well, you have to think about this. You have to be a little bit creative because, there's no 2 anywhere. But what I'm going to do is I'm going to say, well, really what we're given is we're given things in terms of base 2. So if I have a base that's not 2, I should probably change it into a base that is 2. So let me try to say this one. This is going to be log 2 of 6 divided by log 2 of 5. And well, log 2 of 5 is great. I have that already. That's why. Log 2 of 6, well, 6 I don't have yet, but we know that 6 is equal to 2 times 3. Right? So this is log 2 of 2 plus log 2 of 3 divided by log 2 of 5, right? Because this is using the addition rule for logs. 6 is going to be log of 2 plus log of 3. And now these are all in terms of things that we know. Log 2 of 2 is 1, log 2 of 3 is x, and log 2 of 5 is y. That's going to give us 1 plus x over y as the answer. Okay. So none of these has a very, very complicated solution, but maybe aside from the first one, in order to get them, you have to use maybe more than one rule, maybe only one rule. In the last one, we used 2 different rules. And you have to figure out what rule to use, right? And to some extent, that only comes from experience, okay? So a teacher who's been teaching this and has done a lot of problems should have enough experience to be able to kind of figure out, what rules to use for some of these problems that are not quite as straightforward. Okay? So this is an example, it's much harder than just saying what is log base 2 of 8. It's saying you really need to understand the rules in order to make this work. So if something is log 2 of 3 and something's log 2 of 5, can you figure out log 5 of 6? Can you figure out, I don't know, another challenge, can you figure out log base 30 of 300? And the answer is yes, you can figure that out, right? And most of it you can do using a similar method to here. So maybe I'll leave this as a challenge. Challenge for you. What is log of 30, base 30 of 300? Okay, again, in terms of x and y. Okay.
Yes, that of
Yes.
us. Should we
Yes.
answer it now, or should we answer it now, or a bit
No,
later because of time?
Just to think about it. Think about it. Yeah.
Okay.
We don't have time. No. Okay. So the last example I want to say is, example 4, why do the rules work? So this is a straightforward proof question. And as far as I can, sorry, Rosh, did you have a comment?
Yeah, what I mean, I said, we're using that numbers you gave, right?
Sorry, say it again.
Just go back to the question. What I'm saying. All right.
Mhm.
We'll have also log 3 base 2, using that to do the log 300 base 30, right?
Yeah, log 300 base 30. And in terms of these x and y, so x is log 3 base 2 and y is log 5 base 2.
Okay.
Can you figure this out? Okay. All right. So, okay. So the last one, so we have to finish soon, so maybe I won't go through all the details here. Is something we'll think about. We can talk about it next week. We'll prove that, so why do the rules work, right? So if you're going to teach these rules, doesn't necessarily mean that you need to be able to freehand write out a super elegant proof of this, but you should have some sense of why they work. If a student asks you, why is this true? It's a bit demoralizing to be given the answer, it's true because I say so, right? You don't want to give that answer, okay? That's going to turn a student off to math, right? They're not going to want to hear that this is true because the teacher says so and there's no reasoning behind it, right? So if you're going to have a fundamental rule like this, something like log a of xy equals log a of x plus log a of y, like you want some justification for why this is true, at least in terms of exponentials, right? And so maybe I'm not going to write this up as a formal proof, but I'm just going to write it up like this. So I'll say I'm going to call it proof in quotes. It's not very formal, but it's a good enough argument, and it's the kind of thing that, you should know, right? So if, let's say, b equals log a of x and c equals log a of y, then what does that mean? That means that x is equal to a to the b and y is equal to a to the c. So that tells us that xy is equal to a to the b, a to the c, which by the rules of exponents is the same as a to the b plus c. But saying that xy is equal to a to the b plus c, in other words, that means that that the log to base a of xy is equal to, well, that's saying what power do you need to raise a to in order to get xy? And what this tells us is exactly you need to raise a to the b plus c. That's what you need to get xy. So this is telling us that the log to base a of xy is b plus c, which is exactly what you want, right? Because b was log x to base a, c was log y to base a. So this is log x to base a plus log y to base a. Okay? This is the proof. Okay. So this is a kind of proof that if you're teaching this, you should basically know, right? I mean, there's various different ways that you can phrase this. They're all more or less equivalent, but the point is you can turn any rule of logs into a rule about exponentials. Okay, you can turn a rule of logs into a rule about exponentials. And so if you know the exponential rules, then the log rules all come from the exponential rules. The point is that anytime you have a log, you can rewrite it as an exponential. So if log a of x equals b, you can rewrite that as x equals a to the b. And then whatever rule you want to prove, you just rewrite it in terms of exponentials, and it will work. Okay? So taking stock of what we have, right? If I have a student who can do these questions, I might say, okay, they know some basic rules. Okay? And if I have a teacher who can do these questions, I would say, okay, they know some basic rules. But I don't know how much they know, right? Whereas if somebody can do all of these questions, the more difficult numbers and the solving the algebraic equations and knowing what rules to apply to do something a little bit non-straightforward, like log 6 base 5, and being able to write out an explanation for something like this, then I'm convinced that they really, really understand this subject. Okay? And, ideally, as if you're a teacher and you're teaching this subject, you should have a full understanding at this level, even if, the curriculum doesn't give you enough time to get to lots of examples like this for your students. You should still have this understanding, which will be helpful if you're asked about it by students. Okay, so when we go through the different topics that we're going to have, over the course of this semester, we're going to strive to not just get this kind of understanding, but to really kind of explicitly say, what is the level of understanding of this that you need to be able to be an effective teacher for, everybody who's going to be doing this. Okay, so the exercise for the week is not really an exercise. So the exercise is just come up with your own problem involving rules of exponents and logarithms and solve it. And your question should require one of the 4 next level skills discussed earlier. So either something with more difficult numbers, something with algebraic equations, something where it's not so immediately clear what rule you need to apply, or something involving understanding why the rules work. Okay? And I'm going to send out over the chat, I'm going to send out these PDFs of books that I've sent before. So this is a book that I use sometimes. Let me turn off my background so that you can see this a little better. Video. No, wait, no video. No, just back. Okay. So this is a book that I sometimes use. I'm going to send a soft copy. So there's these books called The Art of Problem Solving. And there's a volume 1 and a volume 2. And so I have PDFs of both of them, so I'll send them to the chat group. But this is kind of a math textbook, but it comes from the perspective of next level skills on every topic that it covers. Okay? And so it only covers high school curriculum. It's not doing advanced university mathematics. Everything is high school topics. But it's doing them from this more sophisticated perspective. And in particular, it's kind of teaching all of the topics together. So you can see how all of the different topics relate to each other. Even if you're going to separate them in your teaching, it's good for you to have in the back of your mind, you're teaching one thing, okay, this is related to something else, and so on. Okay, so I'm going to send both of these volumes. I'm going to send both of these volumes to you over the chat room. I see Enoch has how many questions? I mean, as many as you want to. At least one, but of course, if you want to write more, that's fine. We'll go over some of your questions. You can try to stump each other if you want to do that. If you want to try to ask a question to try to stump the other teachers, that's certainly okay. But the point is, there isn't that much you can do to stump people because, there isn't that much going on here, right? So the point is to be able to be flexible enough with this topic to answer anything. Okay? So, all right. So that's all that I really want to say today. So thank you for your attention. I'm looking forward to the program this year. And let me answer Emmanuel's question. Is Emmanuel Che still here? Yes. Good. Let me answer the question that you asked earlier on. Let me just do, why, so in general, we're saying why.
Yeah, I'm still. Hello, Don. I'm
Yes,
still
hello.
here. I'm still here.
Good. So,
Yeah, I'm still here. Yeah.
yeah. Okay. So let me get answers. You're going to ask why is, 1 over 0 and 0 over 0, why are they both undefined?
Yes.
Right. Okay. So let me try to answer this in the most general way possible. I'm going to say, what does A over B mean? Right, when we have a fraction. And what A over B means, so to say that A over B equals C means that it's kind of like a logarithm. So this is why it's a good question, right? So a logarithm, what does log A of B mean? Well, to say that log B base A equals C means that A to the C equals B. You're saying, what do you have to raise A to in order to get B? And that answer is C. Here, what we're saying is, what do you have to multiply B with in order to get A? So what this means is that it means two things. The first thing that it means is that B times C equals A, right? A over B equals C means, well, what is this expression? It says, what do you have to multiply B by in order to get A? Right? That's what a fraction means. So it means that B times C equals A, but it means a second thing. And the second thing is that C is the only thing you can multiply B by to get A. Okay? So it's not just that you can multiply C by B to get A, but it's saying that the only thing you can multiply C by to get A is, the only thing you multiply B by to get A is C. So now let's look at our examples. So 1 over 0 equals C means C times 0 equals 1, right? Clearly, you can't do that, right? You can't have anything times 0 equals 1. So we can't solve. Thus, it's undefined. Okay, can't solve, so it's undefined. What about 0 over 0 equals C? Well, this should mean C times 0 equals 0. Well, that's okay, actually. You can solve C times 0 equals 0. In fact, you have lots and lots of solutions to C times 0 equals 0, right? C could be any real number at all, times 0 equals 0. But that's why we need to look at this second thing. So if you're going to say that this thing has a value, it should be an unambiguous value. Sorry, Miata, I'll answer you in a second. So A divided by B has a value. It should be an unambiguous value. But we're saying that here every C works. So that would be saying that 0 over 0 is every real number at the same time. And that doesn't make sense. We want to say that a fraction should be equal to one number. Okay? So that's why we have this second clause. We're saying that C is the only thing you can multiply B by to get A. In this case, there are lots of choices for C, which violates 2. Okay, it violates clause 2. Okay? And so the reason 1 over 0 is undefined is because you can't find any C at all. The reason 0 over 0 is undefined is because you can find lots of C's, and that's just as bad. Being able to find lots is just as bad as not being able to find any. If you want a fraction to make sense, you have to be able to find exactly 1. You have to be able to find exactly 1. Okay? And so that's that's
Yeah.
why both of these are undefined.
Was?
Yes, Enoch.
Yeah, so the case of A over B equals C. It also in the case where you have 6 divided by 3 is equal to 2.
Mm-hmm.
Yeah, because like you were saying, if you have 6 divided by 3 equal to 2, it means that if you multiply 2 by 3, you will get 6. So it also reversible that you have 6 over 2 equal to 3. Because if you multiply the same 3 and 2, you still got 6.
Mm-hmm. Yeah, it's the same as divided by, right? I mean, it's the same 0 over 0, 0 divided by 0, right? It's all the same thing. And the point is you want there to be one answer. If there's not one answer, then you don't define it. Okay? This is going to be similar to the idea of function, where when you have a function, if you plug in something in the domain, you want it to go to one thing. We talked about this in calculus last time. A function that if it doesn't go to anything, that's not a function. And if it goes to more than one thing, and you don't know what it goes to, that's also not a function. It has to go to exactly one thing. And so this is the similar idea for dividing. There has to be one solution, otherwise you don't define it. Because with lots of solutions, if you want to say 0 over 0 equals 0, well, I could tell you, well, why isn't it 1? 1 also works. Why isn't it 6? That also works. So you can't argue that your answer is better than anybody else's. And that means you don't want to define it that way. You're making to make a definition, it should be the best answer. And there's not a clear best answer here. Okay, so neither of these is going to be defined because either you can't solve it at all or you can solve it in too many ways. Emmanuel, is that clear? Does that answer the question? Is that okay?
Yeah,
Emmanuel?
yes.
Oh, good.
Yeah, it's okay. It's okay. Yes.
Okay, great.
It's okay. Yeah.
Thanks. Okay, let me go. So I see a question from Miata in the chat. So multiply 3 by 5 and divided by 2. Was that equation a constant? Let me find that. Sorry, I'm answering Miata's question first. So Miata's question says, so over here, 3 times 5 divided by 2. Right, it's not really an equation. Yeah, so these are just expressions, and I'm simplifying each expression. I eventually simplify it to log 3 base 2 plus log 5 base 2 minus log 2 base 2. And then since we're given what x and y equal, I'm then just substituting x and y for those expressions. And then here I'm getting a 1. So I don't know quite what you mean by is the equation a constant, but all of these things are constants. We're just writing them in terms of specific constants x and y that are given to us. Okay, so there was another question? Yes, Rash.
So I want to ask, like, what we have 0 divided by 0, because sometimes other people say it's indeterminate, right?
Yeah, indeterminate, undefined. It all means the same thing. I mean, okay, no. Let me take that back. It doesn't mean the same thing. Indeterminate is something that is very specifically a calculus term. It's something that you use when you're talking about limits. So if you're just going to say what is 0 divided by 0, then that is undefined. But if you're saying that you have a limit, which when you punch in the limiting value, you get 0 over 0, for that, you're going to say that your limit has an indeterminate form. Okay, but that's something that's very specific about limits. And when you have these indeterminate forms for limits, there may be other ways to solve the problem by factoring or using L'Hopital's rule or using a graph or a table of values. There's lots of different ways to solve limits that might have an indeterminate form. But that's because you have more information than just 0/0. You actually have a limit of some fraction that is going to give you some information and gives you an answer. If somebody just hands you 0/0 with no context, it's not part of a limit, it's not part of anything, it's just, what's 0/0, then you have no other information. You can't use any of these techniques like factoring or L'Hopital's rules or tables of values or anything because all you have is 0/0. So when you're given 0/0 in isolation, it's appropriate to say that that's undefined. When you're given a limit that substituting gives you 0/0, that doesn't mean the limit doesn't exist. It just means you might need to use another technique yet. So what you say is it's indeterminate because you haven't determined yet what the answer is, and there might be other ways to do that. So that's, I'd say, the difference between indeterminate and undefined, right? Indeterminate means you might be able to figure out the answer. You just need to use your information better. Undefined means you can't possibly have an answer. It makes no sense on its face. It's got to be undefined. No answer makes sense. Is that kind of getting at what you're asking?
Me?
Yeah. I don't know. Did that answer the question the way you wanted? I don't know.
I understand clear.
Okay, great.
So the problem you gave us is just an assignment or just a plain text?
Yeah, plain text. However, you can write it on paper. You can send it to me by email. You can send it to the chat room. People can actually, for this assignment, it would be great if people just send their questions to the chat room and other people try to solve them. That would be a good idea.
So in case like maybe you gotta try, I don't know what I correct. Like I have x plus 2y plus 2 divided by x plus y plus 1.
Okay. Oh, this question here. Oh, I don't even know what the answer is to here. I haven't figured it out yet. So, but you can send me your answer and I'll tell you if you're right. It sounds right, but I haven't actually. I just made this up on the spot, so I don't know what the answer is.
Okay.
I couldn't do it while I was teaching, but I'll do it afterward. Okay. All right. So I'm going to turn off the recording now.